Hello everyone, my name is Zhang Yuhuan, and on behalf of my teammates Weijie, Shu Yao, Yilin, and Canqiu, I present our project, a PV converter with hybrid MPPT and soft switching. Our goal is to convince you of the novelty, feasibility, and significance of our solution for a critical bottleneck in solar power. I will begin with the project's text and relevance. My team will then cover our innovative solution, technical approach, key results, and the commercial feasibility. So, why this project? The demand for renewables is growing, and PV systems are key. But the real challenge isn't just the volume, it's efficiency. In solar power, efficiency is sustainability. Every percentage point saves the lower costs and speeds up a green future. Our project focuses on improving system efficiency by tackling the fundamental challenges holding current systems back. My teammate will now introduce the core challenges.
In this part, I will introduce the two core challenges we faced. The PV curve on the right shows that under pressure shading, multiple local maximal power points and one true global maximal power point occur. As you can see in the figure, traditional MPPT is often stuck at local maximal power points, marked with X in the figure, thus failing to reach GMPP, resulting in significant energy loss, system instability, and increased electromagnetic interference. The other challenge is converter bottleneck. Traditional DC-DC converters suffer from two types of problems: high losses, such as switching losses, leakage inductance energy, and diode conduction losses, and poor output quality, such as current discontinuities, large ripple, and high device stress. These problems reduce efficiency and affect reliability.
And this part is about ZVS soft switching topology. And in this section, we built a converter specifically adapted to this application scenario. By integrating a three-phase boost stage with a three-phase DAB stage, the proposed topology reduces the number of power switches by 6, thus saving volume, cost, and losses while improving both efficiency and power density. Under this configuration, the PV array and the battery can either jointly or independently supply the load. Moreover, the PV source can charge the battery, demonstrating excellent flexibility for solar energy applications. And in this topology, the three-phase boost converter operates with a duty ratio D that splits the input voltage Vin up to an intermediate DC link voltage Vd, which then serves as the input for the DAB stage. The DAB operates under a voltage matching condition and transfers power by means of a phase shift control. The duty ratio D adjusts the amplitude of the equivalent square wave current on the current type side, balancing voltage matching and the trade-off between current ripple and device stress. Meanwhile, the phase shift angle phi controls the phase difference between the two full bridge drive signals, thereby regulating the active power flow. And the figure illustrates the realization of ZVS. Before turn-off, the commutation currently established by phi and the leakage or DC link inductance already flows through the output capacitance COSS of the switch that is about to turn on. During the dead time, this commutation current charges the opposite switch COSS and discharges the COSS of the upcoming device, naturally driving its VDS down to approximately 0. When the body diode conducts and claims the node voltage around 0, the gate is triggered under 0 voltage conditions, achieving ZVS. And as a result, the turn-on loss is almost eliminated. And this topology converts the near-steady DC output provided by the upstream PPT stage through high-frequency isolation and the bidirectional step-up or step-down operation, transferring energy between the DC bus and the battery. It supports bidirectional power flow and introduces soft switching, achieving full ZVS operation and thereby further reducing losses. Ultimately, the system can simultaneously achieve maximum power tracking and the highest conversion efficiency, meeting both performance and energy optimization goals.
In this part, I will explain the hybrid MPPT algorithm and the simulation module. And for hybrid MPPT algorithm, our solution combines two methods to find the max power point. Phase 1 is global scan, phase 2 is perturb and observe. In this page shows the flowchart of the P&O. This algorithm constantly perturb and observe to make power change. For the detail principle, first is initialization. Set initial duty cycle and the perturb step. Measure the initial V and I, and then calculate power saved to P last. Then start perturb and measure the new V and I, and calculate new power. Then compare the P new with P last. If P new greater than P last, means the direction is correct. Maintain this direction in the next term. Conversely, the direction is incorrect. It should be changed in the next term. And repeat this process until find the maximum value. This page is the simulation module. We choose a common scenario as the test condition. The irradiance was 1000 and the temperature was 25. Then look the circuit. The PV array is composed of many components connected in series, and it is connected with a buck converter. And the subsystem should be a microcontroller in practical application. And then the subsystem outputs complementary PWM waveforms to drive the controller, like the picture on the right. And then go back to the circuit. When the duty cycle changed, that means the impedance sent by the PV array changed. So the PV array output V and I will change. And then is a short summary of our work. The process is start from PV array and then adjust by algorithm and the converter. Then give the grid V and I to the ZVS part. After its adjustment, finally the system will give the power to the loads.
Hi, I'm Esther. I'll walk you through the commercial feasibility of our project. Solar isn't the future anymore, it's the present. The global PV market is expanding faster than ever, and the biggest opportunity now lies in making energy conversion smarter and more efficient. That's where we're coming. Our system sits right at the intersection of rapid market growth and meaningful innovation. In solar, every % of efficiency counts. A small gain can shorten payback and increase return on investment across the entire system. Our converter design achieves higher efficiency at competitive cost, turning technical improvement into clear economic benefits. Simply put, it makes solar power more profitable, faster, and it's built to grow. Our hybrid MPPT adapts across multiple PV inputs, while the soft switching DAB keeps high efficiency with minimal loss. It connects naturally with battery storage and EV systems. So what we design today scales effortlessly into the grid of tomorrow. Beyond profit, it's about purpose. Renewables are set to overtake coal within the next few years, and efficiency will define who leads that transition. Our system strengthens that shift, making renewable energy cleaner, smarter, and more connected. Next, we are making the system intelligent, integrating AI-based and predictive control for real-time optimization. We aim for over 99% tracking efficiency and adaptive response under dynamic conditions. This is how we move from efficient hardware to truly intelligent solar systems.
Below, I will briefly introduce our group's division of labor. Shu Yaoliu was responsible for the construction and simulation of the soft switching component, including physical model building and waveform simulation. Weijie Huang was responsible for the construction and MATLAB simulation of the maximal power point tracking model. Yuhan Zhang was responsible for researching the project background and objectives and creates the PPT for this section and the MPPT section. Yilin Gao was responsible for collecting data related to the core issues and creating the PPT about the challenges and soft switching component. Canqiu Dong summarized the completed work, assessed commercial feasibility, refined the future development plan, and created the corresponding PPT. Overall, the division of labor was clear, the cooperation was smooth, and everyone worked together to complete the project materials and presentations.